Okay, hi everyone, and welcome to my talk on embedding and approximation theorems for echo state networks. So this is based on a paper with the same title, and it's by myself and my two PhD supervisors, James Hook and Jonathan Dawes. So let's jump into the contents page. So what this talk is going to be about is, first of all, we'll just define what an echo state network is. So it's a recurrent neural network, or it's a reservoir computer, which takes in a time series data of observations from some process and tries to find a map from that time series to a set of targets. In part 2, we'll look at the special case of the input data coming from a dynamical system. So we'll take observations of that dynamical system, feed those observations into the echo state network, and see what happens there. And this map from the input to the internal state of the echo state network, it's called the echo state map, which we'll call F. In part 3, we'll provide a theorem and proof that this map F is an embedding and therefore preserve the topology of the input dynamical system to the dynamics that govern the internal states of the echo state network. In part 4, we present a universal approximation theorem for echo state networks, stating that any map from the reservoir state to the reservoir space, to the set of targets, can be approximated by an echo state network. In part 5, we discuss the topological conjugacy between the input and output dynamics. So we imagine that if the data that we're looking at are drawn from a dynamical system, which has a certain topology, and then we train an echo state network to predict the future states of that dynamical system, that under certain conditions, this will cause the echo state network to develop dynamics that are topologically conjugate to the original dynamical system. And in part 6, we'll demonstrate all of this theory discussed by training an echo state network on the Lorentz system. And for part 7, we'll talk about future work. So let's jump right into the definition of an echo state network. So to define an echo state network, we have matrices A and Wn. So A is an n by n matrix that we call the reservoir matrix, which represents the connections between the neurons in the echo state network. And Wn is an n by 1 real matrix, or just a real vector, which represents the connections from the input to the neurons. We have var phi, which is a continuously differentiable map on the real valued n vectors, and it's a smooth component-wise squashing function with biases bi. So we can view var phi as a component-wise application of the hyperbolic tangent function with some arbitrarily chosen biases. Then let's imagine we have a sequence UK of scalar observations, or time series of real data points. Then we have a sequence of vectors, rk, defined rk plus 1 is equal to this map var phi, which is like tanh of ark plus w in uk. And these vectors rk are n-dimensional, and they're called the reservoir states. So our first remark is that the reservoir states rk depend on all the previous data points, uk, uk minus 1, etc. So we can view rk as a representation of all the data up to rk. And we have this important property, which may or may not hold for an echo state network, called the echo state property. If the reservoir matrix A has like a 2 norm, and you multiply this 2 norm by the derivative of the activation function, and that product is less than 1, then the reservoir sequences rk and r hat k, which originate from different initial points, r0 and r hat 0, but are driven by the same input sequence uk, then they'll converge to the same sequence. And this convergence is the echo state property, and it holds under this condition. At least this is a sufficient condition to ensure the echo state property holds. So the echo state property was invented or discovered at the same time that echo state networks were invented independently by Herbert Jaeger and Wolfgang Mass in 2001. So having computed the new reservoir states, R1 to Rk, the output matrix W out is fitted to solve this optimization problem. So what we're really doing here is using regularized least squares to find a map from the reservoir space to the target space. So we're regressing against some set of targets. So for the rest of this talk, we're going to restrict ourselves to targets AK that are just observations UK. So the target function, the thing we're trying to do, is approximate the next step in our time series. Now, starting here, having trained the output matrix W out, the reservoir states SK can then be liberated from their reliance on the driving input UK and evolve under the autonomous dynamical system defined like so. So what we're essentially doing here is, once we've got a good enough prediction of our next data point, we can then predict it and then feed that back into the echo state network. And then that gives us the next reservoir state, which can then produce the next prediction for the next observation. That can produce the reservoir state after that. And we continue this process recursively to predict a future trajectory of the system. And we can also view that as an autonomous dynamical system, one that evolves without the need of a driving input UK. And here's a picture that sort of illustrates what's going on in the context of neural networks, or like natural neural networks. So the training phase can be viewed this way. So we have the source of training data, which in this case is just a trajectory of the Lorentz system. We have an observation function omega, which just takes, say, let's say we just take the x components of the Lorentz system. We feed that into the echo state network via these connections Wn. It lands in the reservoir space, and the connections between all the reservoir neurons are represented by this adjacency matrix A, which is the reservoir matrix. In the autonomous phase, we learn this W out, and then all of the points in the reservoir are sent to a single point via W out, and then this is fed back into the echo state network, and then we have this cycle that goes around producing the future trajectory. Okay, so now we're going to focus our attention on the special case of input UK coming from observations of a dynamical system. And this will allow us to define the echo state map. So let's imagine M is a compact manifold and phi is a diffeomorphism on M. Let omega be a continuously differentiable observation function on the manifold M and its output real numbers. We're going to assume our data UK is observed from a trajectory of a dynamical system, evolving under phi and originating from x naught in M, which is just an arbitrary point. So we have this expression here. Then the reservoir state RK, given an initial state R0, is a function which depends on the initial point x, so it's a function of the initial points on the manifold, and it satisfies this relation. And it satisfies this relation by considering how all of these functions are related to each other. So this may look a little bit obtuse, but it allows us to prove the first sort of interesting theorem in our paper, which is the echo state mapping theorem. And it basically says this: as long as the 2 norm of A is less than the min of 1 and 1 over the derivative of phi inverse, then there exists a unique solution which is continuously differentiable of this equation, where f appears twice. And this equation satisfies for any initial reservoir state in the unit hypercube. The sequence of functions here converges in the C1 topology to f as k tends to infinity, and we call f the echo state map. So this may seem a bit abstruse, but f is the map that relates the dynamical system that we can observe via W to the dynamics in the reservoir state, so the dynamics internal to the echo state network. So to provide a bit of intuition as to what this echo state map looks like, I will show you a video. All right, so here we go. So let's imagine on the top left, we can see the Lorentz dynamics. evolving in X, Y, and Z. And we're going to take scalar observations of the Lorentz dynamics. We're only going to look at the X values, which are showed in the bottom here. Now, these X values are going to be fed sequentially into an echo state network as these data points UK, and these are going to create a sequence of reservoir states, RK. So we have RK, which are these long vectors whose dimension is equal to the dimension of the echo state network, which for the purpose of this simulation is 300. And we're going to project those vectors onto the first three principal components, which are the directions of greatest variance. And we plotted that here, and on the top right as the reservoir dynamics. So the map F, the echo state map, is the map from the Lorentz dynamics to the reservoir dynamics. And we've proved that this map is C1, so it's continuously differentiable, which seems about right because it looks like the map from here to here would be continuously differentiable. But it looks like there's more to it. So in particular, the Lorentz dynamics here seem topologically conjugate to the reservoir dynamics. So it looks like this map from the Lorentz dynamics to the reservoir dynamics F doesn't involve any tearing or puncturing of points or anything like that. It looks like a smooth diffeomorphism from one to the other. So a map that's a diffeomorphism onto its image is called an embedding. So these numerical results suggest that F is an embedding, so we're going to try to prove that it is one. And that's the embedding theorem for echo state networks. The echo state map F is an embedding. So our first step towards this was to consider this famous theorem in differential geometry called Tackin's theorem. So what Tackin's theorem essentially says is that if we have a dynamical system evolving on some manifolds, and we are only able to observe, some scalar at every point. So let's say, it's evolving on a three-dimensional manifold, but you're only allowed to look at, one component. So you're only allowed to look at, say, the X component at every point. Then if you have sufficiently many previous observations and you create a vector out of those, out of an observation 1 second ago and 2 seconds ago, 3 seconds ago, etc., and you have sufficiently many of those, then the map from your point on the manifold to that vector of delayed observations is an embedding for generic observation functions and generic observation functions. Sorry, for generic dynamical systems, where by generic we mean that the property holds on a dense open subset. So that's the sort of intuition which perhaps was helpful and perhaps not. But to look at it formally, we'll consider this version of Tackin's theorem proved more recently by Hugh in 2006. So let M be a compact manifold with dimension M, and suppose phi is a twice differentiable diffeomorphism, and has two properties. Phi has only finitely many periodic points with period less than or equal to 2m, and X, if X is any periodic points with k less than 2m, then the eigenvalues of the derivative at X are distinct. Then for any generic twice differentiable observation function, the 2m plus 1 delay observation map, defined like so, is a C1 embedding. So this theorem, as is exactly stated, appears in this paper by Hugh, but the original theorem by Tackin's is here. So there we go. So using that as like a jumping off point, we managed to prove an embedding theorem for echo state networks. And it basically looks like this. So we make similar hypotheses as the one in Tackin's theorem. So if we have a compact M manifold and the dimension of our reservoir is at least 2m plus 1, and we have random matrices A and Wn, and we have that our dynamical system has the same two properties as stated in Tackin's theorem, then for a generic observation function, which is twice differentiable, the echo state map F is an embedding with probability alpha greater than 0. Now, this may seem like a good theorem right up to this point here, where we go, oh, okay, well, we've only proved it for alpha bigger than 0, so alpha could still be very, very low. So the probability of actually having an embedding could be extremely small. And this is a bit disappointing because many authors have found from numerical experiments that F appears to be an embedding much more, well, quite often, like if they choose the hyperparameters correctly, then F seems to be an embedding pretty much every time, which suggests that alpha could even be 1, or at least a number that's quite close to 1, if all the hyperparameters are chosen quite well. So this prompted us to suggest this conjecture, where we essentially conjecture, well, I'll just read through it. So this conjecture says, yeah, let n be a compact n manifold and n a natural number such that n is bigger than 2n. So we have that the reservoir dynamics are big enough that Haken's theorem is going to hold. Let A be an n by n matrix with a 2 norm that's less than this, so that F is C1, so remember this condition from earlier. And Wn is an n by 1 matrix. And we'll let this triple be an echo state network. We'll let omega be a twice differentiable observation function in order to have all the conditions for Haken's theorem to hold. And we're going to let phi be a diffeomorphism on n. And it might require some additional properties, which we haven't specified yet. I'm not quite sure how to prove this. And we're going to let A and Wn be generic matrices in the topology induced by the matrix 2 norm. So in particular, if A and Wn were drawn from a distribution that has full support and satisfies reasonable conditions, then almost surely the echo state map F is a C1 embedding. So that's the conjecture. Okay, so next we have part 4. So many authors, including us, have found in numerical simulations that if we're trying to approximate the future trajectory of a dynamical system, however high dimensional and non-linear the dynamical system is, the echo state network sometimes does a very good job of approximating the future. So we assume that there must be some sort of approximation theorem for echo state networks, i.e. for any target function that we're trying to approximate, there exists an echo state network that can approximate that target function arbitrarily well. So the first sort of step in our mission to prove a universal approximation theorem for echo state networks was to look at one that already exists, which is Hornick's famous universal approximation theorem. So there are loads of these approximation theorems, and this is the one that we're going to appropriate for our purposes. And it's this: if the activation function sigma is L finite, which is a somewhat technical condition on the kind of wiggliness of the activation function, then for all m between 0 and L, functions g on the unit hypercube of dimension n to R, which look like feed-forward neural networks, are dense in the m times differentiable functions on the unit hypercube. So yeah, I should say this theorem has been used to prove other universal approximation theorems for echo state networks, which are similar to the one we present in this paper. For example, one is by Grigorieva and Ortega, 2018, and it shows that if you want to approximate a function and you're free to choose all of the weights in your reservoir matrix A and your input matrix W in and your output matrix W out, then you can approximate any function G. But we want to do a little bit more than this, because in practice, the reservoir matrix A and the input matrix W in are just randomly generated, and these are fixed, and only the output layer W out is trained by least squares. So what we want is to say, oh yeah, if we randomly generate A and W in, then there exists a choice of weights W out such that we can approximate our target function. And more recently, Ganon et al., where et al. Are actually Grigorieva and Ortega again, show a result that's quite similar to this. And in fact, generalizes, in some sense, the result I'm about to show you here, which appears in our paper, which is this, the random universal approximation theorem, as we've called it. And it says this: let In denote the unit hypercube of dimension n, and let F, which is not the echo state map, maybe this is a bit of a confusing notation, be C1 on the unit hypercube. Let sigma be 1 finite, and let Vj and Vj be sequences of IID random variables with full support. So here we have essentially the random terms in A and W in. Then for any probability between 0 and 1, and any epsilon, which is like the tolerance of how close we want our approximation to be, there exists some natural number n, which is the size of the reservoir, such that with probability greater than alpha, there exist real numbers, w1 to wn, which are the entries of the readout matrix wout, such that the random neural network G, defined like this, satisfies this. So what we're saying is, yeah, whatever the target function is, whatever, our target function f we want to approximate, then our echo state network with randomly generated weights can generate, or will approximate f. Okay. So what I want to do now is get up another video. So what we have is that we can approximate any function. So let's say the target function we're trying to approximate is the next step function. Then what I have here is I have a an animation of an attempt of an echo state network to predict the next step of the Lorentz dynamics based on this sequence of one-dimensional observations, and then that observation is being fed back into the echo state network to produce the next reservoir state, etc., to create this autonomous ESN phase. And we're comparing the prediction according to the autonomous phase, which is in red, so this validation data, which is in blue, which is the true trajectory of the Lorentz system. So this prediction in red is what the echo state networks thinks should be happening, and in blue we have what's actually happening. So with that out of the way, what I want to do actually is go right back to the beginning. So what we can see is, first of all, the prediction is following the validation data very well. So we have a good approximation. But then since the Lorentz dynamics are chaotic, inevitably these small differences are going to lead to an accumulation of errors that cause the trajectories to diverge and eventually become far apart. And we can see this start to happen now. But interestingly, the prediction in red, which is the ESN autonomous phase, even though it diverges from the true trajectory, it does remain in the attractor. And it seems to display dynamics that are topologically conjugate to the Lorentz dynamics. And we're interested in why this is, because let's say we all we've guaranteed with the approximation theorem is that we have an arbitrarily good next step approximation. But there's nothing to say that the small errors we get couldn't accumulate to form arbitrarily large errors with the ESN autonomous phase, flying away from manifolds and eventually ending up arbitrarily far. The fact that the manifold is stable and somehow brings trajectories back onto it, and then when the dynamics, the ESN autonomous dynamics are on this manifold, they retain this topologically conjugate behavior. This is not guaranteed by the approximation theorem. So we wonder, why is this? And this next section, that's exactly what we're going to explore. So in order to explore this, what we're going to do is we're going to introduce this idea of a normally hyperbolic attracting submanifold. So to give you an idea of what this is, if you don't know what it is already, we're going to envision a vector field V on the circle S1. And we're going to embed the circle along with a vector field into the plane via an embedding F. So here we have the embedded circle, which is this black loop. And on this black loop, we have these black arrows representing the vector field on the embedded circle. So what we can do is we can extend this vector field on, which is defined on f of S1, onto this open set omega, which contains the embedded circle and which admits the embedded circle as a normally hyperbolic attracting submanifold. So what we mean by this is that this submanifold, which is a submanifold of R2, is surrounded by this vector field which pulls nearby trajectories onto it such that they arrive in this kind of tangential way. So these blue arrows are this extension to the vector field which pulls nearby trajectories onto it. So we imagine that in the context of echo state networks, if we had some dynamics on a circle, and we take these one-dimensional observations of these dynamics in the circle and pass them into the echo state network, and this creates a sequence of reservoir states, then the autonomous dynamics in the reservoir space might be something like this embedded circle with the embedded dynamics. If we approximate these dynamics, which we can do by the random universal approximation theorem, however well we approximate them, we can't guarantee that the trajectory won't slowly just fly off the manifold, right? So we can imagine we take one step and we're very close to the manifold, we have a small error. Take another step, we have another small error, but these two small errors, added up, and now we're a bit further away. And then we take a third one, we end up even further away, and we keep going and we just fly away. So what we want is not just to approximate the vector field on the manifold, but to approximate the vector field on this open set omega, which attracts nearby points back onto the manifold. And that will ensure that we don't fly off to infinity, but that we stay on the manifold. So that's the basic idea. Not to approximate just this black vector field, but this whole black and blue vector field together to avoid flying off. So here are some technical results on normally hyperbolic attracting submanifolds. So the first is that they exist, which is what we want. So we want to say, whenever we have one of these embeddings, we can always extend the dynamical system from the embedded manifold to this kind of ambient space, and then ensure that we have these vectors that bring nearby trajectories onto the manifold. And the statement goes like this: let D be bigger than M. So D is going to be the dimension of the reservoir space, and M is the dimension of the manifold. Let phi be a diffeomorphism on the manifold, and suppose F is continuously differentiable on the manifold. And we're going to suppose it's a C1 embedding. So there exists this open subset omega, which is in, so this should be a subset, not an element of, it's a typo. And eta is a diffeomorphism on omega with the embedded manifold Fm and normally hyperbolic attracting submanifolds, such that the restriction of eta to the embedded manifold is the evolution operator, but just on the manifold. And in order to arrive at this, we essentially followed this textbook by Frank Warner. This next major result is that the normally hyperbolic attracting submanifolds are stable. So it's important that all of the important objects are stable, because with the random universal approximation theorem, we can't do anything better than approximate things arbitrarily well. So we need that all of the important features of manifolds and our dynamics are resistant to small perturbations and therefore stable. So we're going to need to make use of the invariant manifold theorem, which was introduced by Hirsch et al. And the theorem basically states, if K is a compact manifold and eta is a diffeomorphism on K, and it has a normally hyperbolic attracting submanifold, then there's an epsilon such that for any U, which is a diffeomorphism, which is sufficiently close to eta in the C1 norm, so with an epsilon, the diffeomorphism U has a normally hyperbolic attracting submanifold U, such that the attracting submanifold U is really close to this other attracting submanifold lambda. So we need that as well. And with those two things, we can state and prove the ESN approximation theorem. So this is actually an abridged version of the theorem, because the theorem was too big to fit on an entire breadbox. So here's the abridged version. Let alpha be a probability between 0 and 1. Then with this probability, there exists a D, which is the size of the reservoir, with d bigger than n, where n is the a number that's at least 2m plus 1, to ensure that we, well, at the very least, to make it possible that we have an embedding. And we have some matrices, W out, an A and W in, and we assemble them in this funky way. And we have an activation function, which is just tanh again. Then the autonomous echo state network with these parameters that we've constructed has a normally hyperbolic attracting submanifolds on which the autonomous dynamics are topologically conjugate to the original dynamics. And then with that, with this topological conjugacy, this explains what we see in the diagrams and the animations, that the red trajectory is somehow conjugate to the blue trajectory. And there we go. So with all that, we can now demonstrate some of this theory numerically and discuss the pictures that appear in the paper to be specific. So this first one is just a numerically integrated trajectory of the Lorentz system under the canonical parameters that give rise to this attractor. So yeah, this is just to remind you of kind of what it looks like. And this next one is relevant to echo state networks. So to produce this picture, we took one-dimensional observations of the Lorentz attractor. So we just looked at the x components, fed those into an echo state network, produced a sequence of reservoir states, projected those reservoir states onto the three principal components, and those are the training data shown in blue. Then we trained the echo state network using regularized least squares to find a W out, and then produced an ESN autonomous phase, which essentially predicts the future trajectory. And that's the future prediction shown in red, which we can see looks topologically conjugate not only to the training data, but also to the original dynamics, which is consistent with this idea that F is an embedding with reasonably high probability, at least. So what we want to do here is, since we suspect that the echo state map F is an embedding, then there are several topological invariants of the Lorentz system that we expect to be preserved under F. So in the reservoir dynamics, we expect these invariants to be present as well. And one such invariant are fixed points and their eigenvalues. So we searched for the fixed points of the autonomous ESN using Newton's method. And you can see here in black, we have these Newton iterates produced by Newton's method, which seem to converge to this point here, which looks a lot like a fixed point. So the next thing we did was we linearized the autonomous ESN about this fixed point and computed the eigenvalues of this linearization and plotted them in red. So here we have the ESN autonomous system eigenvalues, and we compared them in blue to the three eigenvalues of the Lorentz system, which you can get analytically, and we just looked up. And if we look at this little spot here, we can see that we have the three Lorentzian eigenvalues overlap with three ESN autonomous eigenvalues. And this suggests that the ESN autonomous phase successfully found a embedded fixed point of the Lorentz system and successfully learned its eigenvalues. And we think this is particularly impressive, actually, because if you look here, the eigenvalue is quite far away from any of the training data. So the innermost blue loops are the edge of the training data, and the fixed points is far away from it. So somehow the ESN has inferred the existence of this fixed point and precisely predicted where the eigenvalues are without having actually been near it at all. So in the sort of parlance of machine learning, the ESN has generalized the training data to unseen regions of phase space using kind of topological considerations, I guess. The next topological invariants we looked at and wanted to know whether this was preserved by the echo state map F were the Lyapunov exponents. So roughly speaking, the Lyapunov exponents kind of characterize how quickly nearby trajectories diverge from one another in chaotic systems. So we basically found that the Lorentz Lyapunov exponents, which are shown in black, coincided quite closely to the Lyapunov exponents of, coincided to two Lyapunov exponents of the ESN autonomous phase, which you can see here in blue and in red, which are Lyapunov exponents of 0 and 1. But we found this third Lyapunov exponent of the Lorentz system at -14 didn't seem to closely coincide with any of them. So we're not exactly sure why this is. Maybe the embedding F wasn't quite as good as an embedding as we thought, and somehow this was lost. But maybe this lack of convergence is somehow like a numerical issue. We essentially don't really know why this Lyapunov exponents was not reproduced. It was lost somehow. So it's an interesting question as to why this is. Yeah, our values for the Lyapunov exponents of the Lorentz system, we just took by Sprott, who computed them in 2003. And our method for computing the Lyapunov exponents for the ESN autonomous dynamics was a method that's described in this paper by Derbyshire and Broomhead. So the final invariance that we compared between the Lorentz system and the ESN autonomous phase was the homology of both of these things. So for those of you unfamiliar with homology, homology is the study of the holes that objects have. So a sphere has a big, three-dimensional hole enclosed by the surface of the sphere, whereas a torus has not only this kind of three-dimensional hole enclosed by the surface of the torus, but also has sort of two-dimensional hole that is like if the hole sort of in the middle of the torus, or like the hole in the middle of a donut. You can like pass your finger through to like grip the donut. And the fact that the sphere and the torus have different holes distinguishes them as topological objects. So the important thing is an embedding or a topology preserving map preserves the topology and the homology, or the holiness of an object. So what we need to do is, since all we have is a constellation of data points, is we somehow need to reconstruct the homology of the underlying manifolds using data points. And to do that, we're going to use this tool called persistent homology. So to provide some intuition as to how this works, let's imagine that we have a circle, which is a manifold, and it has a homology group that's given by essentially the hole enclosed by the loop in the circle. Now, let's imagine we have a lot of data points, or there's a lot of points that are just on this circle. And somehow we want to infer from these points that they all exist on a circle. So to do this, what we could do is we could start on all of these points, growing a ball with center at these points. And the ball has radius epsilon, and epsilon grows. So all of these points are now growing their own ball. Once the balls, say, intersect, so we have two balls, once there's an intersection point, we draw a line between the 2 points at the centers of those balls. If 3 balls have a mutual point of intersection, then we connect those 3 points together using a triangle. So now we have a 2-dimensional shape. If 4 points have a point of mutual intersection by these circles, then we connect them all together and form a tetrahedron. And we keep going and build higher and higher dimensional shapes this way. And you can see this sort of happening here. So we have our 6 points. Epsilon 0, they're all separated. If epsilon is 1, then we end up with these points connected. And then we have this loop, which has the homology of a circle. If epsilon is √3, then we have triples of points that are connected, and this creates this lattice of triangles. So now we have an object with a topology of an annulus. And then if epsilon is 2, then every point is connected to every other point and we now have this 7-dimensional shape with all the points connected. So we can see from this example that if epsilon is 0, then it's too short to reproduce the homology of the circle. If epsilon is 1, then we've got, the circle. If epsilon is √3, and then we have a torus, no, not a torus, sorry, an annulus, which also has the topology of a circle. But then once epsilon is 2, then the topology and the homology of the circle is gone because all the points are connected together. So we can recreate the homology of the underlying shape from our data points by choosing the right epsilon. But we don't know what the right epsilon is. So what we can do is bring in this relatively modern computational tool called persistent homology. And the idea of this is to start with epsilon equals 0 and slowly grow epsilon until it's big enough to cover for all the points that we've connected in this one massive shape. So as we grow epsilon, some homology groups or some holes will appear and some will disappear until they've all disappeared and we just have one big shape. So those holes or homology groups that appear and disappear quickly, so they do persist over a large range of epsilon, or they're transient, these are viewed as artifacts of noise and just imperfections in the data. Whereas those homology groups or holes that persist over a large range of epsilon are called persistent homology groups, and these are viewed as true homology groups that really that are true holes in the underlying manifold. So that's a quick rundown of persistent homology. So we applied persistent homology to the driven ESN dynamics, so the training data, the autonomous ESN dynamics, and the original Lorentz dynamics. And these are labeled as blue circles, red downward triangles, and purple upward triangles, respectively. So to interpret this diagram, we have this x-axis called birth and this y-axis called death, and we have these numbers. So these numbers on both the x and y-axis represent epsilon, so the length, the radius of these balls. So let's imagine we have a ball. Let's imagine when we have a ball of radius 0.2, a homology group or a hole appears. And then once epsilon gets to 0.4, then it vanishes or dies. Then that homology group is represented as a point here at 0.2, 0.4. So those homology groups which appear and disappear quickly, or if you like, don't last very long, so they disappear quite quickly after they appear, are going to be near this line. So points that are near this diagonal line are essentially are just viewed as noise. So they're just things that appear and disappear. So these are transient homology groups. Whereas these homology groups well up here, which die well after they're born, are persistent homology groups, and therefore we expect to represent the true holes in our manifold. So we can see here for each of the driven ESN dynamics, autonomous ESN dynamics, and Lorentz dynamics, we have 2 points, and each of these 2 points represent the 2 holes which we expect to see. So in the Lorentz attractor, we have 2 fixed points, and we have trajectories that are around those fixed points. So the homology of the Lorentz attractor is under certain simplifying assumptions. The homology of a figure 8, and therefore just an object with 2 holes in it. So we expect all 3 of these things just to have 2 holes: the Lorentz attractor, the driven dynamics, and the autonomous dynamics. And we see this from this diagram, which is cool, which is great. So you might look at this and think, well, what was the point of doing this? Because we could just see that all 3 of these things have 2 holes. So, why do I need to look at this weird diagram? And that's a completely fair question. So in this case, it doesn't really give you much. But the nice thing about persistent homology is you can apply it to manifolds of arbitrarily large dimensions. So if you have a 10-dimensional manifold and you're interested in the 7, 8, and 9-dimensional holes in this manifold, you can't really visualize that. But in principle, you could elucidate it with persistent homology. One drawback of persistent homology is it's currently very expensive. So we produced this diagram using the software Ripsa, which is a fairly modern and fairly fast, quite efficient bit of software for working out the persistent homology groups. But even to produce this cost about 200 gig of RAM. I was unable to do it on my own laptop. I had to do it on Google Colab, which will offer you up to 200 gig of RAM for free. So there we go. And the last thing I want to talk about is just future work. So yeah, the first thing I want to do is ensure that all the arguments are airtight. So in the paper, there are certain issues with the definitions of things, one of which is that the C1 norm is not, is somewhat ambiguously defined. So in order to clean that up, I think C1 norm should be defined, and we should show that it generates the C1 topology and the C1 norm on the C1 functions form a Banach space. It's for all the arguments that are made to really be justified. And there are some questions around normal hyperbolicity, which, well, yeah, there are sections of the normal hyperbolicity which may not be totally airtight. So we get to sort everything out on that end. The next part of this is to explore when is the echo state map F an embedding. So we conjectured that it was an embedding almost surely for randomly generated A and W in, but this is just a conjecture. So it'd be good to find some necessary and sufficient conditions for F to be an embedding. And it'd be good to generalize all of this theory, which is specific to echo state networks, to a larger class of reservoir systems. And we're currently working on this in collaboration with Juan Pablo Ortega and Lyudmila Grigorieva. So hopefully a paper may come out of that eventually. So the result here is about echo state networks trained by regularized least squares on ergodic dynamical systems. And it basically says this: if the dynamical system is ergodic with an invariant measure mu on an invariant set k, and we train the echo state network on a trajectory in k using Tikhonov least squares, then the ESN will approximate the target function in the L2 mu norm. So this contrasts to the random universal approximation theorem, which is a existence result, which essentially says that for any target function, there exists a set of output weights W out, which yield a good approximation. And this one is a constructive result, which says we can obtain the W out that we want using least squares. A notable difference is the norms are different. So here with the L2 norm with respect to the ergodic measure of the system, whereas in the random universal approximation theorem, we had an approximation in the C1 norm. And the C1 norm is a stronger norm in the sense that all C1 functions are L2, but not all L2 functions are C1. So there we go. The last thing is just a couple of pages of references. So yeah, if you want to pause this and have a look at any of the references, here they are. So here's the first load, and here's the second load. All right, so thank you very much for listening. If you have any questions, feel free to contact me. I'm sure my email is easily findable. So yeah, hope you enjoy listening. All right, cheers, thanks, bye.